Today, I'm presenting generating scientific claims for zero-shot scientific fact-checking. This paper is from Allen Institute of Artificial Intelligence. It will appear at ACL 2022, so it's a very new paper. So as you know, scientific document processing is very time-consuming and expensive because there's need for domain expertise to do the annotation, modeling, and evaluation. Therefore, methods such as zero-shot fact-checking that require less manual effort are very useful. This work works on claim generation to enable the zero-shot biomedical fact-checking. And one of the big challenges for fact-checking is to generate negative examples because fact-checking is essentially answering yes or no, whether it's factual or not, or given a claim and some evidence. So this work proposes knowledge-based informed negations, so KBIN, novel approach to generate refutations. And for the result, the fact-checking model achieves 90% of the supervised upper bound performance in a zero-shot prediction fashion, so which is amazing. So before we dive into the details, there are some concepts that we need to clarify. The first one is called valid claim. So valid claim is essentially a claim that is fluent, atomic, decontextualized, and accurate. Atomic means a verifiable statement expressing a finding about one aspect of a scientific entity or process, which can be verified from a single source. So it does not rely on other things, and it's just one individual aspect. Decontextualized means it requires no original surrounding text, such as pronouns and abbreviations. So it's just standalone. So that's valid claim. And next concept is scientific claim generation. So this aims to generate a claim and given a scientific sentence and optionally some additional context sentences. And it generates one or more valid claims entailed by the inputs. And in the context of fact-checking, claims are supported or refuted by the literature or not enough information. By this, so next, there's an important example. So this work is basically evaluated on the sci-fact task, which is one of the scientific fact-checking tasks. The task is like this. So the inputs are a claim, which is manually rewritten from citation sentences in sci-fact, and with a corpus of a collection of scientific paper abstract. And the task is to first find out the rationales. So find out all relevant abstract and the sentences with respect to the claim. And next, the next task is to predict the stance or veracity in this work to check whether the abstract and the sentences retrieved supports or refutes the claim. For other cases, it's called NEI, so not enough info if the abstract and the sentences are neutral. For evaluation, I will talk about it later. So after given those preliminaries, let's jump into the actual approaches the paper worked on. The paper is mainly working on actually the core part of the paper is generating the claims and its negations. So in this paper, they use the sci-fact authors the claim citation sentence and claim pairs that the sci-fact authors released. And for the source sentences, like basically the input sentence to the claim generation system, they are essentially just the citation sentences. Sometimes it's also called citants. This paper takes two approaches to generate claims. The first one is called claim gen entity. This approach is actually adapted from Pan et al. 2021 from general domain to scientific domain. So the approach is the same, but the pipeline, the actual models are all different. So for this first step, they take each input source sentence, so the citation sentence, and perform named entity recognition to extract the named entities. They use SciSpaCy model, which is trained on Mad Mention's dataset with 4K PubMed, 4K PubMed abstract annotated for UMLS entities. UMLS means Unified Medical Language System, which is a hierarchical system that includes medical concepts. After obtaining the named entities, they use them to generate questions. For each named entity, they use BART to generate the questions. The BART is trained on the SQUAD dataset, Stanford question answering dataset, but in a kind of novel way. So the inputs are actually the answers and the context of SQUAD, the question answering dataset, and the output are the questions. So this is a reversed way to use a SQUAD dataset. After training the BART on SQUAD, they perform inference by taking the source sentence, so the citation and the entity as the input, and the output is the question. Once they obtain the questions, next they convert the questions to claim. So for this, they use another BART trained on QA2D dataset. QA2D contains declarative full sentences paired with questions and their answers from SQUAD. So this is a pretty specialized pre-existing dataset. During the inference time, the inputs are the questions and the named entities they obtained, and the outputs are the final claims. So that's it for claim gen entity. Next, they present the next model called approach called claim gen BART. This works original like novel approach. It's actually simple. So they take the data set of citants and the claim pair released by the sci-fact authors. And for the training, they use the inputs are the citants and the context sentences. By context sentences, they usually take the one sentence and the one sentence before and after each citants. And the outputs are claims. So it's a simple, it's direct prediction model. But during the inference, they perform top K sampling to generate multiple claims. And the K equals to the number of non-chunks in the original source citants. So they also use NER to find out the number of these chunks. Once they obtain the claims, so far the claims are all positive. So the claims are supporting claims. They need to somehow obtain the negated claims to actually perform the fact-checking task. So to do this, they propose the novel knowledge-based informed negation task. System, KBIN. So first they perform named entity recognition, again, to extract the named entities in the claims. And then they take the named entities to link to UMLS meta thesaurus using the sci-spacey entity linker. They select, because remember UMLS is a hierarchical structure. So it's like a tree, but not actually the tree. So they can select the sibling concepts in the concept hierarchy, and they select the top 20 closest concepts ranked by the cosine similarity of CUI to VEC pre-trained UMLS concept vectors. So CUI to VEC, as you may infer, it's just a traditional word embedding kind of algorithm, just like word to VEC and GLOB, trained on the UMLS concepts. So it's just embedding the UMLS concepts to vectors. So once they have obtained the 20 concepts, they next replace the selected entity tags with the canonical names and alias of the concepts. And among the replaced claims, they take the top one, top one low perplexity, so the most fluent candidate claim ranked by a pre-trained GPT-2 model. And finally, they choose a replacement that maximizes the NLI, natural language inference prediction of contradiction with the original claim using Roberta trained on MNLI dataset. So they finally use Roberta to choose the candidate negation claim that is most negated, most contradicting from the original claim. And the figure on the right is the algorithm of KBIN. So essentially, it's the same thing that I explained. So once they obtain both the positive and the negative claims, they start to actually work on the zero shot, the scientific fact checking. So they raise like 3 questions. The first question is, do automatically generated claims enable zero shot scientific fact checking? And for this, they use ClaimGen entity and ClaimGen BART to generate the claims to train a fact-checking model evaluated on the SciFact dataset that we introduced previously by directly taking the Oracle abstract. So it's basically it's a simplified version of SciFact task. So just to recap, SciFact originally retrieves the abstract and the sentences from a corpus of a scientific paper abstract based on the claim. And here in this paper, they assume we already know the Oracle, the gold abstract to work on. And this paper only work on the stance or veracity prediction. So they essentially it's ignoring the rational selection part, which is actually the hardest part. So for the experiments, still about the fact checking, they first create the training data for zero shot setting just using the claim generation system and to generate the supports and refutes claims. They use site-worth dataset to provide the link between the source citants and the support and the cited abstract. And NEI, those neutral examples are generated by taking the abstract of the citants. So remember, we have the claim derived from the citation sentence and the cited paper as cited paper's abstract as the support document. And the NEI, the neutral examples are taken from the cited papers. Taken from the citing papers abstract. So they are kind of closely related, but not the valid abstract to support or refute. By the way, cite worth is essentially just a data set that it's built for predicting whether a sentence is actually a citation sentence or not, given the, if available, given the cited paper. So it's just that kind of data set. And here it's used for linking the citants and the cited paper. For the experimental setup of fact checking, the model is long checker. So this is another model released by AI2. Basically, this paper, SciFact, long checker are all from the same group of people, mostly. Long checker is a long former model, and it takes the claim and abstract concatenation as the input, and it takes the CLS token embedding to predict the stance or veracity. And as a preliminary, fever is the original form of SciFact task based on Wikipedia with larger data sets. So actually fever was proposed first as a general domain fact checking based on Wikipedia, and then SciFact is a scientific domain, scientific or biomedical version of fever. And note that although ClaimGen BART requires claims and as the training data for generating support claims, it does not use any claim evidence pair for fact checking. So therefore, this entire fact checking is still a zero-shot prediction. So next, here's the performance of their fact checking. So let me go over one by one. So the first line is fever only. So it's general domain data set only. So they found fever model, the model trained on fever has a very imbalanced precision recall. So they manually tune the threshold for the decision so that they could rise the recall score from very low level to 66 and essentially balancing the precision recall to obtain a good F1. The next line, SciFact, is the supervised model as an upper bound performance. And as you can see, the bottom two lines are their proposed models performance and their proposed systems performance. And they are both close, and that they both achieve similar F1 performance. And both proposed zero-shot methods achieves 90% of the supervised upper bound performance, which is pretty amazing by just doing a zero-shot prediction. So again, zero-shot means it does not use any of the training set provided by the evaluation task. So next, for the next research question, they investigate the generated claims quality. So here's a metric that they use to evaluate the quality of the claims. They focus on fluency, deconcatenates, atomicity, and faithfulness. So it's actually a hierarchical relationship. So if the first few metrics are low, then basically they discard the examples. So that they can say more time and energy to evaluate the faithfulness of the claim that is worth evaluating. And here's the result. So they hire 3 undergrads, mostly in-domain undergrads, to do the evaluation. They sample biology and medicine sentences from the SiteWorth dataset for this evaluation. So as you can see from the table, claim gen BART is performing better than claim gen entity, mostly, except the atomic, that category. That's because claim gen entity directly produces claims about a single entity, so it's naturally good at atomicity. And the claim gen BART, as you can see, its precision, the last one, the P is higher. So even the proposed, the generated claims, mostly the claims are high quality, so they are valid. However, claim gen entity actually generates more examples based on its nature. So it's kind of a trade-off. And alpha here this shows the agreement is acceptable. Here are some examples of their generated claims. So mostly they are just high quality, and I will skip here. They also compare their generated claims against the manually written claims from SciFact. Remember, SciFact has the manually generated claims, so they can compare it. And again, the root score shows claim gen BART model outputs generates more like better performing outputs. But note that both of them actually are performing pretty well. Both of them are actually at the SOTA level. Next, the third research question is to evaluate the negation quality. So they compare against two baselines. One is entity replacement. So essentially, it's just using NER and replacing the entity with some other entity. And the second one, this paper's title is COVID fact. So it's a COVID-19 paper's version of fact checking. And in this paper, they use like language model. So they use a BART to generate negated claims seek to seek in a seek to seek fashion. So here's the evaluation result. So they again, they didn't explicitly say like who evaluated, but I guess it's the evaluators are the same evaluators as last time. So 3 undergrads, and they just assign entailment scores to each examples, and the higher the better. So the higher the more negation it is. And all 3 methods actually frequently replace the noun phrases, and the KBIN method also replaces verb phrases due to the UMLS concepts nature. So as you can see in the table, so KBIN is overall performing the best. It has higher fluency, and also the negation score is higher. However, from my perspective, there are still many entailments that are many examples that are kind of neutral entailment. So most of like still for three methods, the examples with score of 2 has the most numbers. And finally, they perform a sanity check. So they work on the claim fact checking using only the claim without the support document like abstract. So this is to make sure they don't introduce any kind of spurious features to the generated claim to corrupt the fact-checking task. So as a result, as you can see in the figure 3, the proposed method, so the CG BART plus KBIN is close to the random prediction performance. So that means the label associated bias in the original training data set is actually not present. So, but anyway, they say like the original SciFact training set is inevitably having some kind of spurious feature that is influencing that is kind of cheating, used for cheating in the test examples. So it's just inevitable. And that's it for this paper. And finally, I have some take-home message or some reflections. So I find this paper very cool because it provides potential solutions for many new problems by leveraging the existing data sets for domain adaptation and the transfer learning. And it also implies using pre-trained language models more than instead of a custom architecture also yields very strong performing systems. So this means basically being familiar with the literature and all kinds of resources available is very essential. And finally, the quality assurance is also very important. Like the last 2 research questions, the claim generation evaluation, quality evaluation, and the negation quality evaluation, and finally the sanity check are all important to make sure you don't make stupid mistakes. And that's it for my presentation.